Okay, folks, so carrying straight on from the previous video, there's just a couple short reactions of alkenes that I wanted you to know about. The first of these reactions is what's known as an addition reaction. There are three main types of reaction actually for these sorts of compounds. Addition reaction is the only one you need to know about. Now, if you go on to A level, the other types are an elimination reaction and a substitution reaction. An addition reaction does what it says on the tin. You are adding something to the chemical, adding something to the molecule. So if you're bolting an extra thing onto the molecule, it's an addition reaction. An elimination reaction, you are eliminating something in the molecule, you are ripping a bit off of it. So addition and elimination are the direct opposites of each other. And substitution reaction, just like in a a sports match or something, if you make a substitution, you're replacing one thing with another. So a substitution reaction is where you rip a bit off and swap it for a different piece. So adding something, removing something, swapping something out. But for the alkenes today, we're just looking at an addition reaction. And this applies to all of the alkenes, but I'm just going to teach it for ethene. And it's an addition of bromine. So bromine is a halogen, Br. It's in group 7, which means they go around in pairs. So it goes around as Br2. So how we would write that is Br bonded to a Br. So if you're doing it in a balanced chemical equation, you write Br2. If you're drawing it out, it would be Br bonded to Br. So we've got ethene. So we've got C double bonded to C. Remember eth. So ene because it's an alkene, eth because it's got 2. So ethene. So then we've got H, 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 and H. And we're going to react it with bromine. So bromine's Br2. So we have got a Br bonded to a Br. And it's really straightforward. So all that happens is that double bond breaks into a single bond, which means then, and so like the hydrogens kind of get squidged around a little bit. I'm going to draw them down here just to show me a bit more space. They haven't actually moved in real life because these positions are just kind of equivalent, but so we've got our hydrogens, we did have the double bond, so that's our ethene. The double bond breaks into a single bond, and if you remember, carbons need to have 4 bonds. They did have 4 until I just broke the single bond, so now they've only got 3. And that bond breaks, and then what happens is both of these bromines go down and join on there. So you get Br and Br. So all that's happened is the double bond is split apart and one bromine joins onto one and the other bromine joins onto the other. So we started with ethene and we've added a bromine to it. Now you need to be able to do that for any alkene, but it is just that straightforward. You break the double bond and you add a bromine to each side of it. So if we were going to do it for but1ene, actually just pause the video and try to see if you can draw but1ene, like genuinely pause it and have a quick go at it. That's enough time. Okay, so but1ene. But should have 4 carbons. 1, 2, 3, 4. The ene means it's a double bond, and the 1 means it goes on the first one. So you stick it there. Let's fill in the hydrogens. So we've got 1, 2. This one's only got 1, remember, because it's got 1, 2, 3, 4. Most common mistake is to stick 1 at the top and 1 at the bottom out of a force of habit, but this means that carbon's got 5. So you can draw 1 at the top or 1 at the bottom, but not both. And then we've got, this one needs 2 because it's got 1, 2, 3, 4 bonds, and this one 1, 2, 3, 4, 1, 2, 3, just like that. That's but1ene. That one could have been the other way. And then we're adding bromine to it. So it's just as simple as we break the double bond and we stick bromine there, and bromine there. That's it. So for any alkene, if you add bromine to it, you split the double bond and stick a bromine on each end. Why that is incredibly useful is it lets us use bromine as a test to see if something is an alkane or an alkene. So if you remember, alkanes were saturated, single E, single bonds, saturated. Alkanes were saturated, they didn't have any double bonds. So there's no double bonds to break and add the bromine to. So bromine does not react with alkanes. But with alkenes, as I've just drawn, with an alkene, remember double E, double bond, bromine does react with the alkenes. Now, if you dissolve bromine in water, so it's not reacting it with water, it's just having some bromine, dissolving it in water. So you've got bromine water, and bromine water is orange in colour. So if you stick bromine water with an alkane, it does nothing. It stays the same. It stays orange. If you have bromine water with an alkene, the orange colour, it decolorizes. It goes from orange to colourless. Now this is a word you need to remember. Decolorizes. You can't say, you could say it goes colourless. You cannot say it goes clear or anything like that. They won't accept that. The word to use is either decolorizes or it becomes colourless, because you don't have bromine anymore, because we had our bromine, Br2, or draw it as Br, but when it reacts with the alkene, the double bond of the alkene breaks, the bromine joins onto it, so there's no bromine left on its own, so it can't be orange anymore. So if you add bromine water to an alkane, it stays orange. If you add bromine water to an alkene, it goes from orange to colourless. It decolorizes. So going back to the sort of cheesy little trick to remember it, you've got alkane, single E, because they are single bond and they are saturated. And if you add bromine water, it stays orange. Single E, single bond, saturated, stays orange. Alkene, double E, double bond, and with bromine water, decolorizes. Double E, double bond, decolorizes bromine water. And then the only bit that doesn't work with so double E, double bond, decolorizes, and then it's unsaturated. All right, it's not a perfect way of remembering it, because if it was, that would begin with a D as well, but unsaturated. So summarize all that. An addition reaction, you're adding something to it. So we've got an addition reaction between bromine and an alkene, and it breaks the double bond open, and one bromine sticks to one side and one bromine sticks to the other. So that is an addition reaction. It happens across the double bond, or I use one of my tiles. So if I added bromine to this one, well, first off, you should be able to name this one. I'll give you 5 seconds to do it. Okay, should have got that was propene. So meth, eth, prop, and there's a double bond, so it's an ene propene. If we added bromine, oh, I've drawn this wrong. Spot the mistake. This carbon here has got 1, 2, 3, 4, 5 bonds. This is why you shouldn't film videos at 9:30 in the evening, because you're going to make mistakes when you do it. Right, so now that's it, it's got 4 bonds. So if I added bromine water to this, that double bond would break, and I get bromine joining there, bromine joining there. If I added bromine to this, double bond will break, and I get a bromine joined to that one, and a bromine joined to that one. And if I added bromine to this one, double bond would break, bromine up there, bromine up there. So that's an addition. So we add bromine. Bromine water is orange, react it with an alkene, and it decolorizes it. And the very last bit we're going to talk about in this video is cracking, so cracking is a reaction, it does exactly what it says in the tin. You're taking a massive long molecule and you are cracking it in half. So previously when we learned about fractional distillation, so we learned about the different size chains. And if you remember from the fractionating column, bitumen, which comes off right at the bottom, bitumen is a really, really long chain. Right, and we've got supply and demand. So bitumen, hopefully you can remember uses of bitumen, 2 uses. I'll give you 5 seconds. Okay, so bitumen, hopefully you've said your answer, is used for making roads, making roofs. But in terms of supply and demand, when we extract all the crude oil from the ground and separate it with fractional distillation, we run out of petrol, we sell it. We run out of kerosene, it's all gone. Bitumen, we've got loads and loads and loads of it, and we've got more than we need, more than the demand is for. So if you're running a sort of an oil refinery, you know, you've got 2 million barrels of petrol and it sells out straight away. And maybe you've got 10 million barrels of bitumen and you can only sell 2 million barrels of it. So that means you've got 8 million barrels of bitumen kicking around, you can't sell it. So you do something called cracking. So you take your really, really long chain and you crack it in half. And if you snap it, you're going to end up with a shorter chain alkane. So you take a long chain alkane and you crack it. That was the spring on my camera stand. And you crack it, which means you split it in half, and it goes from a long chain alkane into a shorter chain alkane, which is then more useful. So you've snapped your bitumen in half, and you know, the smaller half, maybe it's petrol or kerosene, and then you can sell that to, you know, fuel cars or sell it to the jet fuel industry or whatever. So you're turning something that's you can't get rid of, you know, you can't sell it, into something where, yes, you can definitely sell that. So you're turning it into something more useful. But if you picture it, and I'm just going to do it on a smaller scale because I don't want to draw sort of bitumen because it's massive. But if I draw 1, 2, 3, 4, 5, 6, yeah, I'll draw one that's 6 long. If I was adding the hydrogens into this, H, 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 H. That's why I didn't want to draw that that's longer because it would take ages. Right. 1, 2, 3, 4, 5, 6. So 6 carbons. You don't need to know this one in particular. It's called hexane. Just like a hexagon's got 6 sides, 6 carbons. So it's hexane. Hex because it's got 6, and ane because it's an alkane. Right, hexane. Let's say if we did cracking on this, and I cracked it, and let's say I split it there. If I was drawing that down here, we'd have 1, 2, 3, 4 carbons. If I draw all the hydrogens, H, 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 and then I've got one over here, C. I've got 2 carbons there with H, 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 and H. And there's a problem now that this is 2 molecules. All carbons need 4 bonds. Well, this one's only got 3. So what happens is this one steals this hydrogen. So if I rub that hydrogen out, it goes over here. So this is brilliant. Meth, eth, prop, bute. So it makes some butane. Perfect. And every carbon's got 4 bonds. But in this little half over here, these carbons have only got 1, 2, 3 bonds. And this carbon's got 1, 2, 3 bonds. So they solve their problems by forming a double bond. Okay? So what we did, we had a long alkane and we cracked it and we made a shorter alkane and an alkene. So cracking takes a long chain alkane and it splits it up and it turns it into a shorter chain alkane, and it also turns it into an alkene. Right, why do we do it? Because we've got more long chain alkanes than we need. We've got more bitumen than we can then they can sell. So when they crack it, they can turn it into a shorter chain alkane where it's more useful, like petrol or kerosene or diesel, something like that. So they turn the long one to the short one, and then the alkene. And the alkene is also useful because we use it to make polymers. That's a separate topic we'll go into. But this is where it's sort of the feedstock for the petrochemical industry. They take the bitumen, crack it into petrol, get to sell it. It also makes alkenes, and that's what they will sell to the petrochemical industry to make plastics and things, plastics and polymers with. And that's it for the reactions of alkenes.